this first row of the ANOVA table is not asking a question about any model that involves awake, but rather it's comparing the equal means model to the model with only sleep total. And so what R is doing is, for each row in this ANOVA table, it's comparing the model that includes all the predictors up to this point to the model that includes all the predictors before this point. So again, for the first row, there's no predictors above it, so it's comparing the equal means model to sleep total only. For this row, it's comparing sleep total to sleep total plus awake. This p-value here, 0.0432, is very similar to the p-value that we got when we looked at the model that had sleep total only. It's not identical, and the reason is that it's using as its estimate of the residuals, residual variance, the residual variance from the model that does include awake as opposed to the model that does not include awake. But the question being asked here is the same as the question being asked above. It's just being asked in a slightly different way. What is the p-value for sleep total compared to an equal means model? So for that reason, the p-value associated with sleep total in this ANOVA, when we run the model on both variables, is not the same as the p-value for sleep total in the linear from the LM output. They're just answering different questions. Again, the p-value for awake is the same in both of these, because in both cases it's comparing the model with sleep total and awake to the model with only sleep total. But this one here is comparing the model with sleep total and awake to the model with only awake, while this one is comparing the equal means model to the model with only sleep total. So why are there so many different tests being outputted here? One way to think about it is that the model itself is determined separately from what questions you'd like to ask about that model. So we specify what model we want. R, or if we really want to use pen and paper, we could. The computer or us will determine the best estimates, or some useful estimates of the coefficients for that model. And then we can ask lots of questions about how surprised we are by the data under a series of different possible assumptions. And depending on what your research question is, you might be interested in different versions of these tests. But it's important to know that even in this case, with these two continuous predictors, you're going to get really different answers to a research question depending on which model you run. And the better way to think about this is you're asking different research questions if you run the model in different ways, so it's important to know what's actually being shown in the output. There is a way to run in ANOVA in R that does not have this problem. Okay, so for example, if I run this line right here, okay, now I have, and it looks a little bit funny, but now I have a row for sleep total and a row for awake with p-values that do match the output from the linear regression, right? I've got 0.864, and here I've got 0.864. I've got 0.868. Here I've got 0.868. Using this kind of funny notation here, then I do end up generating ANOVA output where the order of the rows doesn't matter, and I'm just looking at the whole model compared to the whole model minus one term. So if you are used to using something like SPSS, where this is the default, I believe, then we do have notation that'll get that for us. Because otherwise order matters in the ANOVA. Again, if I show you the results of these two models, body weight on sleep total plus awake, body weight on awake plus sleep total, the p-values in each of these cases, we've got a very small p-value for whichever one comes first, because that's comparing the equal means model to the model with whichever predictor comes first, and a very big p-value for the second one, which is comparing the model with both terms to the model with just one of the terms. So it's really important to know what questions are being asked. Note that we don't have this problem when we just run LM. Right, so when we run LM with body weight on sleep total plus awake versus we run LM on body weight awake plus sleep total, the p-value for awake is 0.868 either way. The p-value for sleep total is 0.864 either way. So if you're worried about order mattering when you're putting multiple terms into a linear model, you're better off using LM than AOV. Better off looking at the traditional regression output than the traditional ANOVA output. That said, There's no particular reason that your research question is about comparing the entire model to the same model without that term. And in fact, I find these p-values, this one and this one, more valuable for trying to figure out which predictors are important. If all you're looking at is regression output that's telling you that neither predictor is significant, you could be misled to think that neither one of these predictors matter. When actually, if you have even one of these predictors, you're doing a great job explaining the outcome. It's just that you don't need both of them. So actually, I prefer this ANOVA output, even though order matters and that's kind of awkward. I'd rather be asking the question one at a time. Hey, does the first predictor matter? Okay, and given that one, does the second predictor matter? Okay, and given those two, does the third predictor matter? Because then I'm going to notice if any of these predictors at all are important, whereas, again, if all I do is put a bunch of things into a regression, look at the output, could be that the particular predictors matter, but I'm not getting significance for any of them. And if I don't notice that the model as a whole is importantly different than the equal means model, I could miss that these are actually very important predictors.